Welcome to MAKE, Hands-on Intro to Engineering Design, a course taught at the University of South Florida. This tutorial introduces to the Arduino Uno board. Okay, let's have a look at the Arduino Uno board. Here is a picture. Let's see what components are on this board. So maybe the most important component is the Atmega 328P microcontroller. Most of these pins are input and output pins. Down here we have 6 analog input pins. They are connected directly to a digital analog converter on the microcontroller. Then up here we have the digital in and output pins. There are 13, but 0 and 1 we cannot use because they are dedicated for serial communication between the Atmega chip and the computer. The pins that have a tilde, so 3, 5, 6, 9, 10 and 11, these pins are special in that they can be operated as a pulse width modulated output. We will talk about that later, but in short, these outputs can be used to create an analog output signal. So we can actually produce something between 0 and 5 volts, while the other pins, they can only be 0 or 5. That is very interesting for certain applications. Okay, so let's see what else is on this board. This is very important, the USB communication, right? That enables all that convenient interaction with the Arduino integrated development environment. Here this is the USB jack. Then we have an Atmega 16U processor. This processor has firmware on it that is able to translate between the USB digital stream and the serial signal that the Atmega chip can understand. These LEDs here, these two TX and RX, they are connected to the USB communication. TX lights up whenever a bit is transmitted towards the USB, and RX lights up whenever a bit is received from the USB port. This LED, named L, is associated with pin 13 via one of those op amps down here to buffer it from pin 13 in case one wants to use this pin for something else than just turning on and off this LED. This is the LED that is being used in the Arduino beginner examples that you can download onto the IDE from the examples menu. Okay, there's one more LED over here. It is a green one when it's lit up, and this LED simply tells us that the board is powered, so it's connected to the 5 volt rail. Over here in this yellow frame we have the power supply components of the Arduino board. The biggest block here, that is the power input connector. The spec sheet says one can apply here between 7 and 12 volts, which are then reduced to 5 volts in this voltage regulator. For devices that need 3.3 volts, there is a second voltage regulator down here, much smaller. This can supply 50 milliamps and is connected to this 3.3 volts output. These two cans are capacitors that decouple the processor from the power rails. What else? There is a resetting fuse at 500 milliamps. So if in case you make a short circuit on this board, the USB port is protected. This fuse is resetting. So after a while, the board should start working again in case this type of malfunction occurs. This here is the 16 megahertz crystal that drives the Atmega 328 processor. Then this switch, that is a reset button. So when you press this, the Atmega is being reset, and whatever firmware is on it is started from scratch. Down here we have the power pins. I just said we have 3.3 volt output. Then there is a 5 volts output, so with this pin you can power external components. Then we have 2 ground connections. In fact, there's a third one up here that is in parallel to this. And then we have a V-in pin. This pin can be used to power the board with a regulated 5 volts supply. So if you have an electronic circuitry you incorporate this Arduino board with, you can directly, if you have 5 volts in this circuit, you can directly power the Arduino board with 5 volts, and you don't have to go through the voltage regulator, etc. In fact, I should point out this voltage regulator only works if you use a slightly higher voltage. This is why they specify one should only put 7 volts as the smallest voltage into this power input. So if you have just 5 volts, you need to connect it here. Okay, now let's have a look at the schematic of the Arduino Uno board. This is directly downloaded from the Arduino website. Let's identify a few components that we just saw on the board. Most importantly, the in and output pins. So these headers are here for the digital pins 8 through 13, and down here we have 0 to 7. And this header is for the analog input pins that connect to the digital analog converter on the board. Blue, that are the power pins. Then with the yellow rectangles we have the 4 LEDs that are on the board. This here is the power on LED, green, and then we have the LED L that is connected to pin 13, and down here we have the 2 transmit and receive LEDs. On this slide I drew some frames around circuitry that has certain purposes. Most important here, what's going on around the Atmega 328 processor. Essentially the processor is directly hooked up to the headers that we just discussed. So here digital and analog and power pins. Then we have some connections over here that go to the Atmega 16U processor that does the USB communication. So we're going through here are the TX and RX pins, right? Pin 0 and 1 digital. So these are connected here to the respective TX and RX pins on on this Atmega chip. So there's serial communication, and then here with these pins, D plus and D minus, we go into the USB jack. So this chip does the translation. Then there's also, this is also pretty interesting, there is a line here that connects between this output and the Arduino reset pin. And so every time you upload a sketch to the Arduino, or you plug it into the USB, there is a reset executed on the Atmega 328P chip to guarantee that it really starts from scratch once a power or once a new sketch is being uploaded. Up here we have the external power input and 5 volt regulator area. This here is the input plug, the input jack. Then we go into a diode that protects the circuit from reverse polarity. We have a capacitor to stabilize the voltage. Then we go into the voltage regulator that makes us 5 volts here at the output, and there's again some capacitance to smoothen the voltage. Over here, that is the switch between external and internal power. Essentially, we have an op-amp that compares what we have at the 5 volt pin, and whenever there is 5 volts either from a stabilized power supply or over here from the voltage regulator, then this MOSFET cuts off the USB 5 volts, right, that come here from the USB connector, and these USB 5 volts are being cut off then, and so the board is powered either from the regulated 5-volt supply or through the voltage regulator. This area here, that is the 3.3 volt regulator, so we go in with 5 volts and then at the output here we have 3.3 volts. The last area to discuss is up here. That is the LED driver for the LED that is connected to pin 13. What we have is one of the two op amps, and this op amp input is directly connected to pin 13. And whenever pin 13 turns on, then the output of the op amp goes high, and then via this resistor the LED is driven, and so it also goes on. The following is a discussion of the in and output pins of the Arduino. Let's start with the digital pins, pins 1 to 13. They're called I/O ports in the Atmega datasheet. In fact, this here is a copy. This is a cutout from the Atmega datasheet. So it's a pretty big datasheet with 250 pages. So in section 14 you find these I/O ports discussed. Here is a schematic of the circuitry that is on each of these pins. So on this side, this is the physical pin on the outside of the microcontroller package, and so we go into the package, and then the first components that are encountered are these two protection diodes. This diode down here protects against negative voltage, so if should one for some reason puts lower than 5 volt, lower than 0 negative voltage onto this pin, then this diode would short circuit this voltage against ground, and so protect the logic on the inside. This diode here does the same against the 5 volts rail, so if we exceed the input voltage at this pin, then this diode here reduces it to 5 volts. Of course, there are certain limits to that. If you would go to a too high voltage, I'm not entirely sure, but it may be 12 volts. If you go higher than 12 volts, then this diode gets fried, and of course then the consequence would be that this input would not work anymore. There's also a pin capacitance associated with all of these input pins. And then finally we arrive here shortly before we go into the logic circuitry of the microcontroller. There is a so-called pull-up resistor that then is connected to a MOSFET transistor, which then connects it to 5 volts. So this pull-up resistor is connected into the circuitry with this MOSFET whenever we select that the input, that the pin is supposed to be an input. That makes sure that if we don't connect anything to the physical pin, so if this would be floating on the outside, that the pin would have a defined state. This connection here would pull it up to 5 volts. If the MOSFET would be off, then the pin would be freely floating. That would mean that this logic here, depending on static voltages that may be present in the environment of the chip, would be somewhere between 0 and 5 volts, but we would not know exactly where. There's one more thing to discuss. These pins here, when they are set as outputs, they can provide up to 40 milliamps. However, due to the output internal resistance of 25 to 40 ohms, we would actually have a significant voltage drop if we would draw 40 milliamps. So it is really good practice to limit this current to less than 20 milliamps. Then that guarantees that the voltage stays above 4.2 volts at the output. As I said before, some of the digital pins can generate a pulse width modulated signal. These pins are 3, 5, 6, 9, 10 and 11. So pulse width modulated signal is a square wave that has a varying duty cycle. So to operate these pins, there is a special command, it's called analog write, which has as arguments the pin number and a value, and this value that determines the duty cycle of the output wave. And so here as examples we have analog write 64, that would give us a 25% duty cycle. If we wanted 75, then we would put 191 as a value. So this goes from 0 to 255, so from a completely off pin to a completely on pin, and we can then in between vary this in 255 steps. The frequency of the signal is constant, right? The only thing that varies is the duty cycle, but depending on the pin, this frequency is either 490 or 980 Hertz. So pin 5 and 6 have 980 and the other pins have 490. Okay, let's see how we can use a low-pass filter to transform that pulse width modulated signal of the Arduino pin into a constant output voltage between 0 and 5 volts. Here I drew the circuit. We have the Arduino pin, which is simulated with a square wave source at 490 Hertz, and we set it to a duty cycle of 50%, so that's a 5 volt square wave. That is hooked up to a low pass filter, at this point consisting out of a 1 ohm resistor and a 1 microfarad capacitor. So this filter has a cutoff frequency right now at around 1 megahertz. So let's see what happens. Let's run the simulation. Okay, I turned on the signal. Let's on the oscilloscope. We now look at the wave. Okay, here we see it. So a nice square wave. Let's see what comes out of the output. So let's turn on that. And we see here in blue the output signal, and so you see the output signal is very much the same like what's coming out of the pin. Now let's drive down the filter cutoff with a larger resistor. So let's put in 1000 ohm, and we see immediately that now the output signal changed dramatically. It is already much smaller amplitude, and it is absolutely not square waved anymore. So that shows us that we simply need to make this resistor bigger. So let's put 10 kilo ohms here, driving down the resonance frequency, the cutoff frequency of the filter further, and we see that the amplitude has was reduced again. Now it's still a little ripple in there. So let's just go to 100 kilo ohms, and we see that now we have a constant output voltage, and it is 2.5 volts. So we are right in the middle here of the square wave that we're putting in. So this filter, you can see, right, it's 100,000, and here we have 1 microfarad. So we get about a cutoff frequency of the filter of around 1.5 Hertz. So it's much lower than the frequency of the pulse width modulated signal. So what we learned here already is the low pass filter must have a cutoff that is considerably lower than the frequency of the pulse width modulation. Okay, so let's play with that a little. So now we have here duty cycle of 50%, right? That gave us an output voltage that is exactly in the middle of the square wave amplitude. So let's go to 75. And we see here at the output that we get 3.7 volts now. Now let's go to 25, demonstrate this concept. And we get an output voltage of 1.2 volts. So you see here, by varying the duty cycle, we can smoothly control the output voltage between 0 and 5 volts, right? If we go here to 100%, then of course the square wave vanished, right? And we get here a constant 5 volts output. So we go to 90%, and we have here 4.3 volts at the output. Okay, the final group of Arduino pins are the analog input pins. We see here a schematic from the ATmega datasheet. Here on the left we have the 6 Arduino analog input pins from 0 to 5. And on the right we have the analog digital converter. So an analog digital converter, all it does is it takes an analog input signal and converts it into a digital output that is proportional. So in this case we have a 0 to 5 volts input range that is translated into a 0 to 1023 digital value, so that corresponds to a 10-bit resolution. And so this value is returned by this function. So the function is called analog read, and it has just one argument, which is the analog pin number. So you could do analog read 2 and hook up an analog signal to this pin, and then the function would return this value depending on what voltage between 0 and 5 volts is connected to pin number 2. This concludes our introduction to the Arduino Uno board. Thanks for watching.